There's an example, you know. And so basically, oh, but usually they put a K in there. I'm sorry. Well, I better not do it. Oh, shit. Sorry, everybody. I'm losing constants. Fuck. Oh, that's it, huh? We're down to one color. Oh, you see a blue pen? Oh, could you grab that? Again, this is out of fashion now. This was fashionable when I was a grad student. It's no longer fashionable. And so I didn't bother to look up the constant, you know, but there's you make gamma k go to infinity. Yeah. And I've forgotten the rate, but if you do that cleverly, you can make sure that you favor see, if gamma k is going to infinity, that what's going to happen is that whichever one of these is bigger is going to overwhelm. This basically, this will converge to 1 for the better arm, and you will explore. So this will, and if you choose things properly, you'll even get the log regret. But it's crappy. People don't use this. I mean, you wouldn't take this to the advertising agencies. It's just not good. So another thing you can do is to stare at that a bit longer.
Is the issue with that, like that approach, that it just takes too long?
Yeah, I mean, empirically, you see it's crappy, and you don't achieve K-star. You know, it's just, you know, there's better approaches. I'm about to show you. Randomization is not a. There's no value to randomization in this case.
Is the construction of the sequence gamma k hard?
It's trivial. Oh, and it's not. I don't remember. That's the thing. I forgot to look it up. The reason I forgot to look it up is it's not relevant anymore. It's out of fashion. So people still do this in reinforcement learning, for in actor-critic algorithms and stuff. It comes up. So we'll come to a case where it's still used. I still think that'll go out of fashion as well. I don't think randomization is really the way to go in all this. But yeah, I mean, in RL, it's so easy to implement that we're still using it. Yeah. But okay. So anyway, so let's go back and stare at this again. And this will be fun. Get rid of the simulation. Cool. So we kill that. We just forget that. Forget it. It's crap. It doesn't work. So we definitely want to enlarge our hacks possibly. Suppose we had suppose we have some notion of conditional variance, say. I'm going to look at it, just a total variance right now. Suppose I had some idea of, so this is a random variable. I mean, take a look. It's a sum of a bunch of random objects in the bottom, top, and on the bottom. So I can take its second moment, and basically we know that, I know we haven't proved it, but you can imagine probably a central limit theorem holds for this as well, at least for the numerator, I mean, forget about this is going to converge to something like n times the probability of choosing this guy, something like that. And this is going to be almost like a Gaussian. So you can look at this sort of, instead of looking at these distributions here, I can look at distributions of the m's, if you like. I hate the fact that, so let me redraw this thing here. Oh no, it's really dead. So that's dead. Oh, Jesus Christ. Maybe if I just turn it upside down for a while.
And just get some pencil.
I don't know if it matters. I think I can make my points in red.
Okay.
Okay.
I see it there.
Yeah. So m hat 1n is distributed according to some mu 1 n, if you like. It's a random variable. But I shouldn't call it mu because there's no averaging done here, so it's a big, fat, messy thing. This thing might be almost deterministic, right? You know, because this is, I mean, again, this is going to converge to M1 if I pull the arms a lot. But let's just say I don't pull the arms a lot, then it's very random. So, so basically, here's 1 again, and it's roughly centered around 1, and maybe still quite fat because we haven't pulled it enough. And then I've got the same thing for the other guy. And I have to wait for it. I gotta take it back. I need another color, I think. Or do I? Now, these aren't densities anymore. I mean, well, no, it's a random variable as a density. I mean, if the original guys had densities, the averages have densities, random variables. And now, it's not really very well, yeah, let's make it really fat tail, this guy. Really fat, and then if I look goes down. It's not Gaussian, you know, I don't know. Yeah.
That might be a better idea to have it heavy tailed on the right side only.
No, what do you mean by better idea? This is reality, it's not. No, I'm trying to illustrate it.
Gaussians, this is only Gaussians.
No, what? No, we're talking about the revenue. We're talking about clicks in the internet. We're talking about Uber. There's nothing Gaussian about real world. No, what are you talking about? Applications or theory?
You mentioned the CLT earlier, so that's Gaussian. Then
Oh, I see what you mean. Oh, yeah, but we're talking about a finite end. There's nothing.
But here
it's
you're
not
constructing something to illustrate.
No, it's finite. The CLT is an infinite end concept. So if each of these guys was exponential or something, you know, then this sum would still be some, you know, have an exponential tail. It wouldn't have a Gaussian tail. You know, it's, right, yeah, yes, that's a fact. For fixed end, it would have not a Gaussian tail. It wouldn't converge like e to the minus, or squared, it would converge like e to the minus r. Okay, so that's a fact. That's just technicality so far from the point. The fact is that if I take a fixed n and I look at these random variables, the tails here will depend entirely on the tail of these WKs, and they won't. And if they have exponential tails, this will have exponential tails. If they're Gaussian, it'll be Gaussian tails. If they're Cauchy, it'll be Cauchy, basically, roughly speaking. So,
But like, do the tails have to be symmetric?
not at all. Why would they? In fact, they can't be because everything's positive valued. Yeah. In fact, I can't let that happen. There's 0. You know, can't be negative. Everything's positive here. So, I mean,
Yeah.
oh no, the noise could be negative.
Oh, well, the noise.
Well, no, we're talking about revenue, so revenue is not negative. I'm not going to let that happen. Anyway, of course, it's not symmetric. Nothing like that. So anyway, so here's a trick that people use. It's the optimistic rule. Fuck that. What I'm going to do is I'm going to look at I'm going to look at the estimated mean plus a standard deviation, or maybe a few standard deviations. For now, I'll make it maybe many standard deviations. Oh yeah, that's right. I'm going to make it. Oh, that's right. I'm going to get rid of the. I'm going to get rid of this. I'm going to basically take this times.
Square root of m.
No.
Or square root.
Shit. Oh my God! Let me look at my notes. I wanted to say this elegantly, and I'm losing track. I'm losing concentration. Well, and also I didn't realize time is flying. Optimistic rules. I would take argmax. I'm gonna leave this vague for the moment, okay? Because really, in the literature you'll find what they do is right away they get rid of this denominator here. They're really looking at the sum. So the gamma n is really related to this. So gamma n gamma ni here. Gamma ni is really going to just be equal to this tin. Oh God, I'm screwing it up a little bit. All right, anyway, so you're optimistic. Yeah, that's not quite it. Oh God, don't worry. I mean, I'll fix this in a moment. I just realized I messed up my notes. But what you end up doing is you say, well, boy, with that big variance, I have a chance. I mean, it could be that it's way out here, and you end up, basically, this here could be that m hat n1. So m hat, we've taken a lot of samples. The mean here really is close to 1, but the variance is huge. And so this, and also I've got the constant, which is getting big as well, which I'm going to have to fix later. And so basically you take the one with the biggest mean plus a confidence bound there, whatever is bigger. And so with this one with a smaller variance, the guy was over here. That should be a 1. And that looks like a square. I'm sorry about that. All right, so I'm going to wrap this up because we're out of time, and I want to show you a pretty picture. What you end up doing is this. We know the rate of convergence is, we know that the error between m hat in and m and the mean, there's a central limit theorem that is going to hold. And like the expectation of that thing squared is roughly just 1 over the number of sampling times. And even without the squared, but
Bias term.
no, the number of samples. Oh, there's a mean there. I mean, even without the square, but forget it. We know that the rate of convergence, the mean square error in an estimate, if this was n, if I was just sampling this over and over again, this would be, and there's a sigma squared there. If I was just, suppose that Ti of n is n, okay, so I'm just pulling the ith arm over and over and over again, then you can, because these guys are all IID, you can just work it out, and you've got the top is n times the variance of one term, and the bottom is n squared, when you square it is n squared, so you get a 1 over n. That's how it happens. And you can show in this generality, as long as you're pulling these things without viewing the future, you're still going to get, instead of 1 over n, it'll be 1 over the times you pulled. Okay? And so, so this is what you end up as your surrogate for this guy. And you might have a constant here. So this is consistent. So this, at least for large n, this expectation is approximately mi. So so you take that as a surrogate, and this is just some number. Maybe you just take a constant, and people in practice just take this to be 10 or something. And but this is the thing you take it as your surrogate, and then you get what's called the UCB algorithm. And I didn't write it down because it's so much in my brain. How could I forget it? But allergies do that to you. So the UCB algorithm. I'm just going to go in and cheat.
The Berkeley algorithm.
No, because they try so hard to con people into thinking that's true. They really do. I mean, it's nothing to do with Berkeley.
It's good computer science.
Nothing to do with Berkeley. It's called the upper confidence bound algorithm. Upper confidence bound. It's such fraud. I mean, every single professor at every university will say UCB algorithm. That stands for upper confidence bound. Unless you're a Berkeley professor, you say the UCB algorithm, and you write it down. You never tell them, and it is. Oh fuck! I blew it. Oh, Jesus. Okay. So it's exactly this. And then it's just I'm getting confused about that R. I mean about the thing I'm going to add. Fuck, where is it? Oh yeah, so oh boy, so put a question mark there because I did screw up everybody. Sorry about that. Here's actually what they will put in. So I'm going to square this. I want to take the square root of this. So I'm going to have so it makes sense to have a square root of Ti of n in my trick. And I'll just write this down and we'll talk about it next time. Sorry about screwing this up. There's my gamma n. So remember I said I'm going to have a big constant there? It's not actually that. There is my gamma n. It's like square root of 2 log of n, and I'll explain that next time. It doesn't have to be 2. It could be a sigma I squared there. Would make sense as well. So you're taking a mean, and instead of 1 standard deviation, you're taking the square root of log n times the standard deviation. So you're going way out there, potentially. All right, and there it is. And so this is an algorithm that gives you the log regret, that I mentioned. All right, and I just have to do this with you, so we've got time. All right, so I'm sorry that I screwed up the. It takes too long. For 2 things happen. 1 is I forgot to write this down in my notes, and 2 is to justify why you get a square root and a log there is another hour lecture. Because you have to talk about large deviations bounds, and we're not going to do that. So basically, you have to explain how far in the tail am I going to go, how many standard deviations, and it turns out the square root of log n is just right, so things will work out. And the constants don't really matter. So I could stick in a square root of it. It would make sense to put in a variance term here as well, but it's not necessary. Okay, so what's going to happen is that you're going to if you don't pull an arm a lot, this thing here grows, and so this will blow up. The means are in the real world. They're 1 or 10 or whatever. If I don't pull an arm, this is a log n, it's going to blow up, and so eventually I have to pull it. But also because it's an argmax, these guys are going to equalize. You can imagine that. At first, one of these, for one eye, it'll be much bigger than the other, so you'll always pull it. Then they equalize, I'll pull the other one. And they're going to start fighting each other. So this algorithm is sort of, they compress together. And so I wanted to show you, if I have time, because it's not, I want you to be motivated to play with this when you get home. An online simulation of this. Because when you watch it happen, you can really believe why it works. Oh boy. Oh, that's right. And then the power, is this it? Or is it? No, right here. And then canvas. Okay, so announcements. You will see courses. Why do I have to choose? Announcements. And there you go. So here's this thing. So you can see 2 things here. First of all, you can see there a link to a tutorial by my buddy Tsaba, who's a DeepMind, and also we're co-organizing this thing at Berkeley. If you click that, you'll see a much better tutorial on Bandits than what I gave you here today. I would even have skipped this lecture and said, watch that, except I need to tie things together. I need to say, here's a POMDP, it solves a Bandit problem. Oh wait, it doesn't. So this is only. So the second half of today's lecture, in a way, I wish I could have said, watch this, because he does a very good job. But then his co-author, who's also a deep mind, came up with this game, and let's play it. So you go to this game, and then you do two things. First of all, you click the standard UCB algorithm, which is what you have there. Okay, so this is the algorithm, the decision rule. And then you also click display. Display means the confidence bound, and for some reason it's doing something funny. Huh. I have no idea why it's initialized this way. Maybe if I click new data, what happens? Okay, so basically we're starting out with, I don't know how it's initialized, but basically there's some initial mean of 0, you know, and then there's the top there, maybe it's beyond the screen, is the confidence bound, and perhaps they're equal, I don't know. And so these are two arms, and you don't know which one's better. Maybe you like red over blue, and you think this is better, but we don't know what the means are yet. Oh, that's right. Actually, we can. The dashed lines are actually the means. So actually, we know the blue guy's better, but we're not supposed to see that. You know? Okay.
The agent doesn't know.
What's that?
The agent.
Yeah, the people. Yeah, that's right. This is behind the scenes. So if we, I'm going to I'm going to do one step at a time. Well, I'm going to click run and just watch carefully what happens. You can see it. You can see the confidence bounds moving down. Every time a confidence bound moves down, it means you pull that arm, because whenever you pull an arm, this thing goes up. So the confidence bound goes down. Because the mean here doesn't change very much. that moves around, but eventually it sort of stabilizes. Okay. All right. See, this confidence bound is equalized. And you can see that you pulled the arm with the, wait a second, we're minimizing? Oh fuck, this must be backwards. This must be trying to minimize cost rather than maximize reward, because it's pulling this arm all the time and got that mean. So it must.
The blue one 74 times.
Oh wait. Are you right? That's right. No, you're right then.
So
now if it's pulling this more, then it must be that we're trying to maximize the reward. But what's strange is, why is it? I thought that this was the upper confidence bound, and that was the mean, conditional mean. I mean the empirical mean.
So
let's try it again.
That makes sense why the orange has a wider bar, because...
Wider bar, yes.
Right. But
why is it meeting the dashed line? Well, that is not. That's what's confusing. So let's run it longer and see what happens. Oh, first let's run it again. New data, run algorithm. Oh, and now I see. It's such a short run. It's just a short run. So that was a really rare event, that we got such a crappy estimate of the mean. See, as far as I understand it, this lower thing here is the empirical mean at stage n, and the upper guy there is this, the sum of the two, and so it would be, given we only had 15 pulls on this arm, it'd be very strange to get a good estimate of the mean, and so we don't have a good estimate of the mean. With 85 pulls, we get a good estimate of the mean. I don't know how before we didn't. And so you can keep playing with this and see what happens. New data, run algorithm, and see what happens again. And both of them a little off in the mean, but so that's only after 100 time average of 100. If you go to 500, new data. What's fun is that one won't convert. So even after 500 samples. Even after 500 samples, it's quickly realizing that this is a stupid arm to pull. The confidence bounds you see are matching up on top, and they'll keep on equilibrating, but you're never going to pull this guy again. I mean, you're not going to pull it as soon as these guys, sorry, I said something stupid. As soon as these guys meet, you'll never pull it again. That's what I meant to say. Let's see that. I mean, well, you'll have to, but you'll pull it very, very rarely. To see this, let's really watch it happen. We have to make a really big horizon to really get an estimate. So the confidence bounds are meeting, and they're always going to stay together. So you do have to pull both arms. You're pulling them both. But you have this huge lack huge band here because you're pulling the arm so rarely, and so you're keeping that uncertainty huge because, and so you're pulling the arm, you don't need to pull the arm much. And it stopped, and we didn't quite get down for the confidence bound to hit 0.65,
The final numbers of the estimated means.
I don't know. I guess the number. Yeah, I guess so. I guess I wasn't sure. But yeah, it must be because this is 0.3, and that makes sense. That's 0.24, I guess.
I don't get why the blues. If you hit new data, you see the blue is initialized higher than its mean, but the orange is initialized below.
Oh, the initial condition, I have no idea how they did that. They just drew some random crap.
What you said earlier in the lecture was whether or not it's Bayesian or non-Bayesian matters a lot.
No, I'm saying it doesn't matter at all. No. When you get to bandits, it's irrelevant. No, you throw it away. No, you misunderstood my point. I'm saying that if you stick to a purely Bayesian and really assume you know B0, you're screwed because then there's nothing to do. If you knew B0, that'd be so.
I'm talking about X0. So how you initialize this, whether or not that's random or not.
Yeah, that's B0. That's right. That's a Bayesian setup. So a pure Bayesian setup where you know B0 doesn't make sense because then there'd be no reason to use a POM-DP. The policy would be open loop. U star would just be a constant. You wouldn't need observations. And that was my point. Yeah. So there is Bayesian bandits, but you don't use a Bayesian filter. You run a filter like this.
So this is doing UCB, not the optimistic thing.
No, the optimistic is silly. No, there's only
UCB.
UCB.
Okay.
Yeah.
Can you not combine them to do UCB with optimism?
No. Oh, these guys are the same.
No, there's another algorithm.
No, that was stupid. It doesn't work.
No, optimism?
Yeah, it doesn't work.
Why? It seems fairly...
No, you mean this one with the sigmas.
Optimistic rule, yes.
Well, that's almost the same. I mean, you basically fool around with this. It's the same thing. Yeah. This is too hard to compute, but you know how to approximate it, so you put in that approximation. Yeah. So you could come up with an algorithm with a conditional variance. This is not useful because you know how its statistics, you know how it grows, and since you know that, might as well put it in those numbers. It doesn't help you. Yeah. So I know there'd be questions because this is a lot to digest very fast. So, but there's no this is motivation, but it's not used. Yeah. Anyway, so that's something to play with. I mean, if you fool around with this some more, you'll get more intuition, and you'll again, you see there's always this residual confidence error on both sides. In order to pull both arms in for the off-end, it's always going to have to be positive. It's never going to be actually zero, and these are going to just slowly go down. But just because that's huge and that's tiny, you can be pulling like mad here, because every time you pull this, that thing jumps down a lot. So, so you pull it very, very rarely, as you see, 62 compared to 1900. Yeah. So it's cute, and I mean, I introduced. I'll turn it off. I'll do it in a second. I introduced the. I introduced this not because it's sort of a classical thing in this literature, You're not going to let me turn off. Ugh. How do you I don't know how to log off, so I'll forget it. How do you turn this fucker off?
So you know how to use the remote.
But okay. No, this is for a TV of some sort. Anyway, so I introduced this not because it's a standard thing used in Bandits. It's because it's the kind of thing I want you to think about when you come up with hacks in RL or whatever, is that I want some statistics as a surrogate for my belief state. And it makes sense to look at a conditional mean. It also makes sense to look at a conditional variance. That's really it. And in Bandits, they remove this by surrogates because of these sorts of relationships. But I think that it could be really fun in RL to take junk like this as features for cooking up algorithms. I think it's one way to go. So we'll get into that later on. Might play around with that. But I think that's it. Yes. I guess